Good afternoon, folks. It's 4 o'clock. Let's get started. I would like to introduce today's speaker, who is our own Professor Sascha Kempf. Let me give you a little bit of background. Sascha was an undergrad at Humboldt University in Berlin, graduating in 1994, before earning his PhD from Friedrich Schiller University in Germany in 1999, and later his habilitation in 2009 from the Technical University in Braunschweig, Germany. After a postdoc at Friedrich Schiller University, he took a job as a research scientist at the Max Planck Institute in Heidelberg before joining CU Physics and LASP in 2011. Sascha was the deputy principal investigator of the Cosmic Dust Analyzer instrument, which was on the Cassini mission to Saturn, and is also the principal investigator of the Surface Dust Analyzer instrument on the Europa Clipper mission, which is going to launch to Jupiter's moon Europa in October of next year. He's also been the co-investigator on countless other instruments and missions from NASA and its European counterpart ESA. Sascha has given talks all over the world on topics related to cosmic dust and planetary systems and the evolution and origin of our solar system. And we're honored to have him here today to talk about some new insights into the age of Saturn's rings. So please join me in welcoming Sascha Kempf.
And we can down the light. Okay, so as a space dog, we need a dark in the room. Okay, so what I want to report to you today is an answer to a very, very old question. Yeah, and this is, how old are Saturn's rings actually? So when I started as a research scientist at Max Planck, and my boss told you your new instrument is the Cosmic Dust Analyzer on Cassini, go to JPL, get your training, yeah, and I showed up there. The first person I was running into was Jeff Cassie, who is one of the co-authors, and he told me, yes, this is the question you guys have to answer. How old are the rings? And I was like, how we are even supposed to do that? Yeah, and eventually we managed to do that, and let me tell you about that. So let's start with one of these wonderful Cassini images of Saturn's rings. And we really have come a long way. And what I want to say with that is that Saturn's rings played more than once an important role for the evolution of modern science. So it all has started with Galileo Galilei, who was the one who discovered the rings. Yeah, so he used a rather crappy telescopes to do that. So there's not much good to say about the Inquisition, except that they were really into red tape and into documenting and to keep record of basically everything. And so we still have 3 of the telescopes Galileo used I think one is at the Vatican, one is at the University of Padua, and I forgot what the third one is, but we still have the telescopes. We can try to repeat the observations of Galileo, and it's difficult. Yeah, it's really challenging to actually spot in the images Galileo acquired what he basically claimed to be present in the images. So, and what Galileo observed, this is in his own drawing, is this. It doesn't really look like a ring at all. Yeah, and what he realized is that if we repeated the observation, let's say a year later, it looked different. Yeah, so this is what the sequence of figures is actually showing. Yeah, so he had no idea what it is. And he called these structures ANSA, the ANSE Latin for handle, yeah, because to him it appeared like handles, right? And this is how we still call the outermost tips of a ring in an astronomical observation. Yeah, so Galileo was the discoverer. Now I ask our knowledgeable friends from the astrophysical department. I have no idea. Yeah. So you know it, friend? Yeah. So, but the real issue was not so much things like aperture and focal length. The biggest challenge at this time was the quality of the glass. Yeah. And so the way how they manufactured these telescopes were by trial and error. Yeah? So Galileo didn't know what it is, but Christian Huygens figured it out. Yeah, so he was not only the discoverer of Titan, he also figured out what Galileo actually observed. This is now from his book, and he figured that this is a projection effect, yeah, and that what has been observed is actually a ring. And here the wording is important, a ring, one ring. Yeah? And people were actually very excited when Galileo announced the observations and when Huygens gave his interpretation, because the fact that a stellar object, yeah, and at this time it was still considered as a kind of a stellar object, yeah, that something spherical, beautiful, is now matched with a structure which is not spherical. This what meant a big deal. Yeah? So it had implications for how to look at nature. So, and things got worse. Yeah? So Huygens figured out that there is one ring, and Giovanni Cassini, the namesake of the Cassini mission, he actually figured out it's more than one. So what he observed was that there is a gap in the ring structure. And this made matters worse. So he was the royal astronomer for the French king. And the French king was pretty much annoyed. Yeah? And basically what happened was that he provided Cassini with a list of topics he was allowed to talk about in public. Yeah? And this list neither included, the rings, nor did it include, the sun. He also did work on the sun. Yeah? So people were really concerned about that. Okay, so, but at Cassini time, starting with Cassini, people know that there's more than one ring of something. Yeah? And it was basically the picture that those rings are made of probably a metal. Yeah, but what everybody agreed about was that the rings are solid. Yeah, some solid piece of something which for magical reason are tied to the planet. So, and it was Maxwell who figured out that this is not possible. So this picture is from a time when Maxwell was in his 50s. Yeah? He did this work when he was he just graduated from university, and he had to find an income. Yeah? So there were no funding agencies at this time, and so he participated in an essay contest. Yeah? And the winner of the essay contest got awarded with enough money to basically cover his expenses for the next year, and he won this contest, and he wrote this contest, his essay about Saturn's ring. And he figured out that this whole idea that these rings are solid, this is not possible. Yeah? There is no material with the tensile strength which is sufficient to sustain the Kepler shear, the fact that more innermost material wants to move faster than the outermost material. Such a material just doesn't exist. And he concluded that this ring structure must be composed of boulders which are orbiting the moon, the planet. And he also, which is not, I should have copied this out as well. He also figured something else. He figured that if this is the case, if this is an assembly of bodies orbiting the planet, then these bodies will undergo collisions. And if they do that, this means that at this point I will start to transfer, to export angular momentum. Yeah, so, and if this happens, this thing has to start to spread. Yeah, this is nothing that can prevent the boulders from doing that. And so he already concluded that there must be a limited lifetime of the ring system. And what he actually did in his essay, he started a whole new area of physics. It's basically what we now call kinetic fluids, yeah, and viscous and dissipative fluids, yeah, and dissipative evolution of such structures. So this was the starting point. And in this sense, Saturn's rings did it again. Yeah, they started basically a new area, a new field of research. So the fact that the rings are not solid implies that their lifetime, their age, their lifetime has to be limited. How short? That's a very good question. Yeah, okay, so then the next 100 years, more or less, happened nothing, yeah, until close before the Voyagers arrived at Saturn. So what was not known at this time was what are the rings actually made of. So in 1960, this was not known. So there were candidates, yeah, but it was not like that we had any evidence for that. But at the end of the 60s, spectroscopic observations of Saturn's rings became possible. Yeah, and when astronomers trained their mapping spectrometers onto the rings, they obtained spectra, and the first publication about that was by Professor Kuiper, yeah, the namesake of the Kuiper belt, and he concluded, wonderful infrared spectra, looks like ammonia. And about a year later, Carl Pilcher published a paper in which he showed that, yeah, ammonia looks kind of like that, but water fits better. And this fact itself, you know, has basically started my lifelong mistrust of any planetary observations using infrared mapping spectrometers and stuff, because this whole is so ambiguous. Yeah, so if you actually look at those spectra, yeah, this is what they recorded, and I think on the bottom are the lab spectra of ammonia and ice. They are not so different, right? At around the time when the Voyagers arrived at Saturn, we knew that the rings are made of ice, of water ice. 95%. This is where the Voyagers helped out. So they basically told us, so we got better optical data from the rings. So the rings have a tint, yeah, a color, and some other Voyager observations told us basically that it's 95% water ice, and I will tell you in a second why this is actually kind of surprising. Yeah? But before I do this, I should tell you that planetary rings are actually not rare. All icy giants and Jupiter, they have rings. So in the case of Jupiter, it's the Gossamer rings, so you have to have a very specific orientation of the observer relative to the rings to actually see them. Well, the Saturn, obviously, Saturn has rings. Uranus has rings. That's a Voyager observation, a Voyager image, and so does Neptune. So rings are not rare, yeah, and it's actually rather easy to create a ring. All it takes is that you have to put some mass into the Roche zone. That's the zone around a planet where the gravity, where the tidal forces dominate. Yeah? As soon as you put some stuff into this region, yeah, it will get disrupted, and it will get dispersed, and it will end up in a ring-like structure. So there is not really a surprise about that. Yeah? But Saturn's rings are unique. And they are unique in two ways. On the one hand side, Saturn's rings are incredibly massive. Yeah, so they are optically thick, or at least a part of the rings is optically thick. Yeah? This means you cannot send a ray through the material. Yeah? So that means that you cannot determine the mass of the rings with optical instruments. Yeah? You have to do something else. So they are much, much more massive, the rings, and they are clean water ice. And so what is the problem with the clean water ice? Yeah? So if you want to create a ring like Saturn's ring, which is its mass is roughly the mass of the moon Mimas. Yeah, that's the innermost ice moon in the Saturnian system, 500 kilometers diameter roughly, I think to remember. Yeah, so if you put Mimas into the Roche zone of the planet, you would end up with a ring like Saturn's rings, but bodies of this size, they all have rocky cores. Yeah, that's part of the evolution of the solar system. This is how you form such moons. Yeah, you form them from a common reservoir of icy planetesimals and of rocky materials, and then you clump it together, and if you wait for long enough, the rocky material will segregate to the center of these icy moons, but you end up with something which is icy on the outside, rocky at its core, and we can actually measure how much of rock is in those bodies. Yeah, so Cassini did this. How do you do this? Very easy. You determine the mass of the moon, and you determine the radius. Yeah, and if the density is larger than 1, yeah, this already tells you, what else is in it. So, and all of these bodies have, which are large enough to create a ring, have rocky cores, or they are just dirty ice. Yeah, one out of the two, and it's difficult to understand how you take a body which contains, let's say, 20%, 30% rocky material, and you end up with a clean water ice ring. Yeah, so this was realized quite early, that we have a problem here, yeah, and that's what's remarkable about Saturn's rings. They are massive. If you run a calculation for the dissipative evolution of such a ring, yeah, you end up with a problem to explain why the ring is still there if it has been formed together with the planet. So, of course, the way to wiggle out from this problem is to claim that you have started with an even larger ring, an even more massive ring. You can do that, but bodies which are even larger contain even more rock. Yeah? This is, but there are ways to do that. But on the other hand, now the ring is not only very massive, it's also very clean, and so you have a problem. Yeah? So, and at this point, the question of how old are the rings actually become really important, because this tells us not only about how the formation of the Saturnian system happened, it also tells us about what may have happened later. Yeah? What is the reservoir of potential bodies if such a ring is young to form it later. And so it's a lot of very, very useful constraints we can derive from that about an evolution of a planetary system. So that's the driver. Okay, and now let's come back to the 95% of water ice. So 95% is fine, but what are the other 5%? Yeah, and that's a good question. So again, this is a wonderful image from the Cassini. It's a false color image of the rings, where the color itself tells you something about the albedo of the ice. And what it tells you is that it varies. It's not a constant across the ring. You actually have a variation of the albedo with the point where you are on the ring. And people have done a lot of work to actually kind of reverse engineer these photometric information. What are potential candidates? And the range is rather wide. Yeah? So there are colleagues still insisting what we see is nanophase iron. It's not entirely clear how it ever should have ended up there, not to speak about 5%. Yeah? But again, it's a match. to some extent to the spectra, but the best candidate is that it's silicates and that it's some organic material, which makes a lot of sense because there is one process which is basically creating or providing a constant flux of mineralic stuff into the system, and that's the micrometeoroid environment of the solar system itself. You can't switch it off. Yeah? And this compound of material is composed of mostly silicates. So, okay, so that's just, to wrap it up. So why does this 5% matter? So it tells us about the ring formation, tells us about the ring age, as I will show you in a second, and it also tells us something about the ring particle dynamics. So let's dive into that. So let's naively assume that, as hard as it may be, the rings have started off as a clean water ice ring, nothing else than water ice. Then it's a valid question to ask, okay, how long would it take for polluting flux to change the color of the rings such that we basically match the current state of the rings, or that we have enhanced the mass of the non-icy stuff by micrometeoroidic or by meteoritic material only? Yeah, so in order to do that, you have to know the flux, the mass flux at infinity. I will tell you in a second what this actually means. Yeah? But if you would know this, you could naively do the following. You could say, okay, I want to accumulate 5% of the ring mass. If I know the flux and if I know the area of the rings, I basically integrate until this number has been matched, or this number is matched by the accumulated stuff, and this is the pollution age. Yeah? Way too simplistic. Yeah? So it does not really work this way because the ring will lose mass. Yeah? There's other type of evolution, but the idea is really like this. Yeah? So if we say we start with a clean ring, then the mass flux will clearly provide us with an estimate for the time it takes to make them dirty. Okay. So in order to do this better, we have to have a closer look at the fine structure of the rings. So that's a high-resolution Cassini image. Yeah? And when you zoom in, you see structures like that, and that's a density wave. That's created by a resonance with one of the smaller moons outside of the A-ring, Prometheus. And that's a density wave. And then there are also bending waves, which are marked here. That's where the red bar is located. That's a resonance with minus. Yeah? And a lot of this structure, of this fine structure we see in the rings, is due to resonances. Yeah? And our colleagues have spent a long time to basically identify the producers of all of those wiggly structures in the ring. Yeah? But as it turns out, that you cannot explain everything by that. There's other structure in the ring which you cannot create just by resonances. And that's shown, before I show you this, here's a picture where you see on top the albedo, the optical depths of the rings. And you see this huge jump between the A and the C ring. That's the B ring. Here the ring is optically thick. Yeah, so the fast photometer on Cassini, the UVIS instrument, of which Larry was the PI, is then not any longer able to observe the star, yeah, which provides the light they have used to do these radial scans. And you see the ring fine structure very well in these optical depths profile, but you also see that you have these very sharp edges. And these very sharp edges, they are hard to explain just by resonances. Yeah? How do you do that? And this has been discussed even before the Voyagers, yeah, that basically the meteoroid flux acts like a kind of a razor, yeah, and it's sharpening the edges and it's doing other stuff. The other stuff the dust must do is to basically create this color pattern. Yeah, so without this mechanism, you would end up with a smooth albedo across the ring. There must be a process which is distributing the material in a way that you end up with a very constrained albedo pattern, and this process is the ballistic process. And ballistic transporter, let me show you the original drawing explaining what's going on from the paper from Cassini and Estrada from more than 25 years ago. So the idea is as following. The micrometeoroid hits some ring material. Two things are happening. So there is a transfer of angular momentum. Yeah, the area is large. This actually plays a role, and this means that this causes the material to spread out. At the same time, you create ejecta, yeah, basically stuff you splash up by the fast impact, and those ejecta can now either rain down on other parts of the ring if the opacity is high enough, yeah, or they even fly through the ring if there's a gap, yeah, and return to the side of origin on the other side. And so by means of that, you set up this complicated pattern, yeah, where the transport is controlled by the local optical depths at this point, and then you can run computer simulations, and you can model this process, and you can, based on that, figure out how long does it take and what does it take to create the pattern we observe now. The color pattern and the formation of certain structures which you cannot create by other means. And so what I always found interesting is that in these models, so one thing they calculate is that for the flux we consider here, it would take the micrometeoroid to completely remove the ring material from a point in the ring within about 2 million years. Yeah, if there's not a process replenishing or redistributing the material. Yeah, and when you run these computer simulations or these models, and you end up with this Drake-like equation, yeah, which gives you now the age of the ring in terms of some wonderful parameters. So let me quickly walk through what these parameters are. So we have the sigma naught, which is the surface mass density of the rings. And this equation is actually normalized to the newest values we have of all of those parameters. The mass of the ring is basically the mass of the B ring, the part which is optically thick. And because it's optically thick, you cannot just use optical methods to determine the mass. And this was something Cassini managed to measure during its last orbits. Yeah, in order to do that, you need actually to fly the spacecraft over the ring, and you have to measure the gravitational perturbation of the rings itself onto the spacecraft. And by means of that, you get the mass. And I remember that we actually had a bet going on, yeah, where everyone could basically bet on his or her preferred mass, ring mass, yeah, and the closest proposal wins. I forgot who won. Cassini won. Okay, good. He's the co-author. Yeah. It's difficult, and it turned out that the mass of the B ring is 0.4 Mimas masses. Yeah, so about 50% of a 500-kilometer ice moon. So the next number is the meteoroid flux. This is what I basically will tell you about. Yeah, this is what we measured. Then we still need to know what is the density, the bulk density of the incoming meteoroids. Yeah, because what we measure is actually size, not mass, and so this has to be addressed. And the number that's used here, 2,800 kilograms per meter cubed. It's the average mass of cosmic silicates, more or less. Yeah? So that's not really critical. The next number is an interesting one. That's the gravitational focusing factor. I will show you in the next slide what it actually means. It's an important number. And the last one, that's a kind of a fudge factor. Yeah? This eta basically says what fraction of the incoming flux we actually assume to contribute to the ring color or to the pollution of the ring. Yeah? So we could have said all of them, yeah? And this would probably have made some colleagues suspicious. And so we go with 10%, which basically addresses all potential shortcomings which can happen in this process. Yeah? So if we would have assumed 100%, the rings would have been 10 million years old. Okay, so the gravitational focusing. So suppose you have a flux of something, and this flux of something is approaching a planet. And you are an observer at the radius r2, and you know the flux at the radius r1. So there are two extreme scenarios, and the first one is the concentric infall. This means you basically, your particles have zero velocity at r1. This means they only feel the gravity. Yeah? They're all attracted on straight lines. And this then means that the flux the observer at r2 will observe is scaling with the surface of the shell, yeah, of r2. In other words, the observer at r2 will see an enhancement of the flux by r2 divided by r1 squared. That's the largest possible gravitational flux enhancement you can possibly observe. And the other extreme case is the opposite. You have a fast stream of particles. They are so fast that they couldn't care less about the gravity. Yeah, they are not affected by the gravity of the planet itself. And the observer at r2 would observe exactly the same flux as at r1. And then there's the middle ground, right? That the particle, the flux, the mean flow speed of the flux is in between 0 and infinity. Yeah? And this problem can be solved. It has been done by Bepi Colombo. And there are actually two phenomena which increase the flux. The first one is that the particles get faster just because of gravitational attraction. But the second one is that the streamlines get closer, yeah, because it's concentric. And both effects increase the flux. And now the question is, by what factor is the flux increased when the particles arrive from infinity at Saturn and they are collected on the rings? Yeah? And this number, this factor Fg, this factor depends on the speed of the meteoritic flow at infinity. And both numbers were not known, the flux was not known, and the speed of these particles were not known. And in this sense, we also needed to determine the speed at infinity. Okay, and we did this with this wonderful instrument, which experienced a happy death in Saturn's atmosphere a few years ago. That's the Cosmic Dust Analyzer I had the honor to work with. It's an impact ionization detector. So it's, in this sense, a similar instrument than the instruments which were on Galileo, on Ulysses, and on even older instruments. But this instrument, for the first time, also included a time-of-flight mass spectrometer, which allowed us to constrain the composition of the particles hitting the detector. And what's important for this talk, this large structure here in front of the instrument, this grid system in front of the instrument, that's a velocity trajector. That's, in detector which allows us to determine the velocity vector of the incoming particle before this particle hits the instrument. Yeah, and that's the game changer. And this is what has been used to measure the flux. But before I do this, let me just brag for 2 minutes about the other achievements. So the CDA instrument has really contributed significantly to the Cassini success. This is fair to say. So we have contributed to the discoveries at Enceladus. Actually, the plume itself showed up in our data before our friends from the imaging team even knew that there is something like that. And we had a wonderful time when 3 instruments tried to make sense of their data, and everyone was reporting something weird, which was not belonging in the data set. And eventually we figured out that there must be an emission from this part of the moon. And we also contributed significantly to the understanding that there must be a subsurface ocean on this moon, because we basically collected particles from these emitted by the moon, and we determined their composition. And from the composition, you get the evidence that this must be actually frozen droplets from a boiling interface between the ocean and the vacuum, and we even found later organics into that. But we also contributed to other parts. Something which is very close to my heart is that there's also a diffuse ring outside of the main rings. And this is actually the region where Cassini spent most of its time. And we were actually tasked to do measurements over there. This ring is supplied by Enceladus. And that's a wonderful NASA story. Yeah? When Cassini was in the design phase, NASA set up a committee of the leading specialists in how these diffuse rings work. And they were asked to provide NASA with realistic numbers what they need to design for, meaning how many particles and how large is the thing. Right, Mihai? And you guys did a good job because you were off by orders of magnitude. And unfortunately, these numbers have been used to design the instrument to tie down certain instrument parameters. And so what we actually found is that there's much more of this stuff. The stuff is much tinier than we thought, and that the distribution in this system is actually not symmetric. And the fact that it's not symmetric is complicated, because this tells us something about the dynamics. And this, to explain this, is really difficult, because this involves plasma physics and some assumptions about the field setup in the system to actually enforce this. Okay, but now let's come to the flux. So what we did, we used the trajectory sensor, which works incredibly well for material that's charged. So there's a setup of 4 grids. The innermost and the outermost grid is grounded, and the 2 inner grids are attached to a charge-sensitive amplifier, and they are inclined. So when now a charged object flies to such a structure, you end up with an asymmetric feature, like here. This is actually a recording from the lab. Yeah? If the particle flies through like that, we get a structure like that. First, the amplitude of this feature. This is the mirror charge of the particle. So we directly measure the charge the particle carries. And plasma physicists will tell you that if you know the charge and you know the potential, the plasma potential at this point, you get the size. Yeah? And you measure actually also quite accurately the size. So, and this again is a flight data recording. So the larger the particle, the larger the charge, the easier to detect the feature. This is one of these features. It's a fit to that. This corresponds to the trajectory like that. So we have measured the trajectory. And this is a projection. And because of size limitations to the instruments, we can only measure 2 out of the 3 speed components. Yeah, in order to measure independently the third component, we would have needed another inclined grid. Yeah, and then the instrument would just have been way too large. Yeah, but we can constrain this component as well, though there is this dip here. And this dip is caused when the particle is in between these two sensitive grids, because only when the particle is exactly in the plane of the grid, the mirror charge will be reported completely by the grid itself. If the particle is here, some of the field lines will connect to the grounded walls. Yeah, and this leads to this dip, and this can be calibrated out. Yeah, how the depth of the dip depends on the distance to the wall, and we have done this, and this gives us another constraint. And the last constraint we get from the time of impact, where at the hemispherical target, at which point of the hemispherical target has the particle hit the target, and from that we get a solution set which at maximum consists of 4 solutions which are compatible with the feature. 4 different velocity solutions, and for each detection. And then we did the following. For each of these detections, we followed the trajectory of the particle. Yeah, so we did a backwards integration, including the gravity of all the moons and all the other players. And now there are 2 possibilities. If the particle reaches the hemisphere of the planet, the hemisphere is the radius inside which the gravity dominates over of the planet dominates over the gravity of the sun, then the particle was actually launched from outside of Saturn. So then this particle is contributing to the mass flux. But if the particle is not doing this, if the particle is basically ending up on an ellipse, never reaches the hemisphere, then the particle is a bound particle. So this is basically how it works. And we knew this, but it's still a challenging measurement because it's a needle in a haystack problem. So the Cassini CDA has detected something in the ballpark of 2 million particles. And 163 out of them are actually of non-Saturnian origin. Yeah? So it's a very, very small number. Yeah? And so you have to find them. So it's a challenge to data processing. The only good thing is that because larger flux means younger ring systems, so if we miss a few of them, yeah, then we overestimate the age of the ring. Yeah, so in this sense, we are safe. And we can then use some assumption from plasma physics to get the mass. So, and once we did this, you do all these necessary steps to verify if this all makes sense. Yeah, and one of the things you do is you better verify where you have detected the particles, if there are suspicious patterns. Yeah, and that's one of them. So the spacecraft itself, the color code actually is the time the spacecraft spent there. Is much faster closer to the planet than at larger distances. At the same time, the gravitational focusing takes care that you will detect more particles here than here, yeah? And this all has to be factored in. So that's why the best way to verify that is to basically run a prediction how many for a given flux of these particles you would expect to detect within a radial bin, and this is shown here. Yeah, this is our detections, and the black curve is the prediction for the gravitational focusing factor we have found from the speed distribution at infinity. So it's a pretty good match. So the data is consistent. There are no artifacts in the sense that we over or underestimate the flux at certain points. So, and then the last thing I actually wanted to show you is, even if you have found your 163 particles, how do you actually calculate the flux from that? Yeah, that's not easy. Yeah. So naively, again, you would say, okay, I take all the I take the mass of all particles, I sum them up, and I divide them by the sensitive area of the instrument. Correct this for the angular field of view of the instrument, and I multiply this with the observation time. Yeah, this is a flux. But if we do this like that, and you can just see it here, then we ignore completely that there's something like gravitational focusing. Yeah, so it's much more likely to detect a particle closer to the planets at a larger distance because the flux gets amplified. So we have to address this. Can we do this? We can. We can do the following. We can basically replace the observation time by the time it would take to observe the flux at infinity. Yeah? So if, for example, I'm here and the gravitational factor is 5, yeah, then I can say, okay, this is the same measurement as if I would have done this at infinity at a 5 times longer time. So, and this is what the integral means. You basically factor in the entire trajectory of the spacecraft, and this also accounts for periods when we have not detected anything. And are we good? We are goodish. Yeah. So with this, we are already very close to a real number. But there's still something we have ignored here. And that is that the spacecraft is moving relative to the isotropic flux. Yeah, there is an aberration effect. So when we were at this point, when we realized that we have to account for that, I was like, we can ignore this because this somehow averages out. Yeah, and my colleagues were like, no, you can't ignore it, yeah, because you never know. And you can actually treat this rigorously, and this is the time when you remember your kinetics from plasma physics. You can completely describe this by a kinetic problem. Yeah, now the sensitive area is a vector, and you have to deal with all these distribution integrals. Yeah, and this integral now contains basically the aberration of the spacecraft. So I just want to show you that it's not just simplistic, summing up masses. Yeah? And with that, we get the mass flux. So, and I told you we had for each of the particles, we have up to 4 velocity vector solutions. And not for all of those detections, all of the 4 solutions actually were on the path out of the hemisphere. Yeah? That's why we grouped them. If we just count for the particles which only have exogenous solutions, yeah, we end up with 76, and we have a flux of this magnitude. And we take this as a lower bound for the flux. Yeah, that's the worst case scenario. And then we do the opposite. If we take all, then we have the upper bound for the flux, these 2 numbers. And those numbers are about a factor of 2 lower than the flux, which has been reported before, which was based, by the way, on a completely non-physical model for how the particles even come to Saturn, yeah? Because it ignored the gravity of Jupiter. But the game changer actually is that the particles we detected are really, really slow. Yeah? So they are basically spiraling in. Yeah? And it's the low speed of the particles which leads to this large gravitational focusing factor. And this gives then this number here. So if we put the flux into the Drake equation, yeah, we end up with something like a few 100 million years. Yeah, so this is what you get from the meteoroids record. Every parameter is conservative. This means that the rings we observe now have not been formed with the planet. This does not mean that the planet has not started off with a ring. It's just not the ring which we observe now. Yeah, it's a different one. And this is consistent with the measurements of the ring mass by the radio science system on Cassini. It's also consistent with the radar observations of the pollution degree of the rings. And it's also consistent with the dynamical evolution of the ring moons. So it's a completely independent thing. So people actually have backtraced the evolution of the moons in the Saturnian system. And they are not stable. Yeah, from time to time, Dione switches orbits, Tessis and Mimas, so it's a dynamical problem. And it shows actually that according to these dynamical studies, the moon system of Saturn is also dynamically young, yeah, whatever this means. Yeah? And so there is now very, very strong support that the rings are young. And so just give me another 3 minutes to give you some other takeaways. So because we measured the velocity vectors and we propagated the velocity vectors into the interplanetary space, we also know now all the orbital elements of these particles, which actually have contributed to the flux. And this allows us to tell you something about what is actually the source of those particles we encounter at the Saturnian orbit. So this is shown here. That's a diagram which shows the semi-major axis and the eccentricity of the detections. The inclination is color-coded. Yeah, and so we have actually a group of stuff, so particles in this range here. Those are particles which are consistent with the Kuiper belt origin. So those particles are actually migrating inwards from the Kuiper belt. It's the same population of particles Mihai's instrument on New Horizon has observed. The grayish stuff here, that's the model prediction by Andrew Poppy. So that's quite consistent. Then we have another family here with the green colors, which are basically on very high inclinations. So those particles, they are not moving in the ecliptic plane. They are at an almost at a right angle with some of them. And those particles are actually consistent with an odd cloud body origin. Those are particles which are on highly inclined orbits with very large semi-major axes. Yeah? And that's probably the first time that we really have detected something from an odd cloud object. Yeah? Because the irony is that to my knowledge, we have not observed a single odd cloud body yet really being in the odd cloud. Yeah? So we have evidence that some bodies have to originate from there. Yeah? But it has not been observed. And then we also have a number of particles in our data set which are actually not even bound to the gravity of the solar system. So, and the last two slides. So a few takeaways. So one of the takeaways is that you actually, if you want to know something about the composition of Kuiper belt objects, you don't need to go to the Kuiper belt. Yeah? It's sufficient to have an instrument which can measure the velocity vectors and the composition of the meteoroids migrating inwards, as long as you place this kind of observing satellite outside of Jupiter's gravity boundary, yeah? Because Jupiter acts like a wall protecting the inner solar system from stuff from the outer solar system. So that's a good thing. And we are actually now able to build much, much better instruments to do exactly this job. Yeah? And this is what we call a dust camera. So Mihai proposed a mission to NASA where we actually wanted to use such an instrument to basically decipher the entire meteoritic complex at an Earth orbit position. And such an instrument consists of two parts. One is a trajectory sensor on steroids. Yeah, that's this thingy here. So Zoltan Stanovsky has invested a lot of time to develop such detectors. They are basically wire detectors, like in high energy physics. And now you measure the image charge on individual wires. And this allows you to really reconstruct the 3D trajectory of the particles. You can do this very, very accurately. And with that, there's no ambiguity whatsoever. What is the origin of the particle? And it also tells you about the mass. And the other part of the instrument, the compositional analyzer, tells you what is the composition of these particles. So in this sense, such a dust camera is really a camera. The particles are the photons, and it tells you something about the site of origin. And the optics, the trajectory, tells you about where the particles have been launched at. And then the other thing I wanted to show you, what you also can do is you can use these trajectory sensors doing very close flybys at moons, where you produce surface ejecta in large amounts. So let me show you that. That's the instrument which we just delivered to NASA, and that's exactly what the instrument is doing. So let me show you a simulation. So when you do a close flyby, these ejecta are produced by meteoroid impacts all the time. The closer you get to the surface, the more of this stuff you will observe. And the instrument is actually measuring the velocity vector and the composition. And by means of that, we can trace back every single ejecta to the surface. And so this means we have ground truth in the instrument. We can actually tell you that this particular piece on the surface of the moon is made of this particular stuff. And if we are happy and we find amino acids or stuff, then we have evidence that it's actually a good candidate for habitable systems. And I leave you with this image. So we have delivered the instrument. It's just integrated. This is how it looks. It's the golden thing on top of it. And I'm so happy that we actually finished the instrument and I don't have to worry any longer. So thank you.
Okay, we have time for a couple questions. I saw a hand right in the front. Shoot up, please.
Great talk, Sascha. So what are some hypotheses about the event that formed the rings?
Complicated. Well, I think we still have to bet on that it's a kind of an outlier. That for some reasons there are still existing clear water ice bodies somewhere, and it was just a lucky event. But the planetologists will figure it out. But the thing is, actually, whatever the answer is, it's always complicated. Either you have to explain how you create something very clean when the system has been formed, when all the material was mixed in the planetary disk. So that's even harder to do that. So I don't really have a good answer to that.
But there must have been some interaction between something outside Saturn's pre-existence with what was already there.
So people have actually done experiments like using the Nice flux, so the meteoritic the planetesimal bombardment 500 million years after the solar system has been formed. They just had the stuff, in a Monte Carlo-like fashion, flowing into or streaming into the system, and they checked if there was, a kind of a lucky shot, that you shoot an icy body with a rocky core into the Roche zone, and then for some magic reasons, the rocky core gets kicked out. It's a very, very rare event. It's possible, but it's not. So I'm honestly the wrong person to ask.
Tyler, yeah. Sure, why not? Like a TV.
Thanks. I was wondering, how much would you expect the flux of micrometeoroids to change over time?
That's a good question. And we wondered about that for quite some time. But as it turns out, the flux is actually quite stable. That's because of, you have to explore what is actually the reason that there are micrometeoroids in the solar system. And this is because of the parent bodies which are shedding those particles. Yeah? And these parent bodies, their number and their orbits have not much changed during the last 4 billion years or so. Yeah? And the orbits of such micrometeoroids are also quite stable. So it's basically impossible to change anything on scales of 50 million years or so. Yeah? So that's not the way to wiggle out here. It might even be so that the flux was a bit larger at earlier times, but this would not help the case, right? So, yeah, that's.
So I'm looking at 5 o'clock on the clock, so I'd like to respect everybody's time and wrap it up. If you have other questions for Sascha, please come down to the front, but why don't we thank him one more time. Thank you, Sascha.
Thank you.
It was a nice talk. I like that.
Thank you. Hey, good to see you.
So glad to see you.
Yep.
I'd like to introduce George, who has just written a paper on Saturn's rings, measuring the optical depth using